Hello everyone. Now we're going to speak about. If my PowerPoint turns on. We're going to speak about trees and graphs. Basically, a subject that is very, very widely used in computer science and computing, and basically everything you're going to do from now on if you're planning to be a programmer, or even quality assurance or support or whatever, doesn't matter. You'll most probably use them. So we'll talk about several topics. First I'll check if my Zoom it is on. We'll start talking about trees first. What's a tree besides an apple tree and something else tree? We'll talk about what are trees in programming. You've probably heard by now of some types of trees. We'll talk a little about implementation. We won't cover the subject in whole. You will most likely not need it that much. Meaning that whenever you need some kind of tree or graph or something like that, mostly trees, graphs you can implement. But when you need trees, fast trees, well implemented trees, you will most probably use something from the internet, something for power collections, for example. Then we're going to talk about graphs, what is the connection between these two, etc. So, tree-like data structures, first topic for today. We'll discuss a little about the terminology on what is a tree, what is a node, what is an edge or a connection. As I said, we're going to speak a little about how to implement these trees, but only theoretically. We won't delve too deep into these things because they're pretty complex. If you can implement a balanced binary search tree, you probably can compete at an international level. It's not very easy. It's not easy at all. We'll talk about traversing trees. What does that mean? How we can walk through a tree and how we can visit the nodes of each tree. We'll talk about balanced trees, the thing I mentioned 5 or 6 times today. And then we'll talk about graphs. And keep in consideration that each tree is a graph, but a special type of graph, not the opposite. Okay. So, trees. Not this type of trees. Other types of trees. What are trees? Mathematicians say they're branched recursive data structures. What I say is a tree is this. It has a root. This thing is called a root. And this root has leaves. Well, not exactly leaves, parts of it. These things, after the root, are called its children. So these things are children. And these children can have other children and other children, and this thing can have more than one children, and this can have, for example, 2. This can have only 1. So, what's important here? This thing is the root. These things below the root are children or nodes, depends on how you name them, and the things at the end, the nodes, all of this we'll call a node. The root is a node, the children are nodes, everything is a node. These things are edges. And every node which has no children we'll call a leaf. Because everything in the tree which is at its end and doesn't have any branching left is just a leaf. So, yeah, you can imagine these things as green. This one's green, this one's green, this one's green, and this one's green. So, that's basically how a tree would look like abstractly. How it will look like in a computer, well, that's a more complicated matter, and we'll discuss it later on. So, what we said, recursive data structure, meaning that each tree has a root, each root has nodes, and each node has children. And each child is also a node, which can also have children. Or can not have children, depends. So, some examples of trees, and this is actually wrong. This is some example of graphs. Doesn't matter, that's too much theory to practice. So, a tree you can have a binary tree. What is a binary tree? A binary tree is a tree which has at each parent only 2 children. Exactly 2 children, not only 2. So this thing over here would be a binary tree. This thing like this is not a binary tree. So a binary tree, exactly 2 sons for each vertex. Sometimes one less. You could have one node which has only 1 child for a binary tree, but that's rarely met. So what can you visualize with the tree? Well, you saw that the tree structure is something like a network, because you have some things, and these things are connected. You have one node, another node, a third node, etc., etc., etc. This thing is actually called a graph. Well, it's not called a graph yet, but from this moment onward, it's called a graph. When you have a tree, we saw what the tree is. When you have a tree with a cycle, and this thing is called a cycle, because you can go in a loop through all these vertices all the time. This thing is called a cycle. When you see a tree with a cycle or a loop, it's called a graph. So maybe we should say what's a graph. A graph is any system of connected things. Doesn't matter what those things are. These things can be cities connected with roads. These things can be the sewage system connected with pipes. This thing can be the numbers connected with the relation of multiplication and division, and for example other things. So a graph is basically anything that looks like this. Nodes, these things are nodes, nodes, and these things are edges. The red things are edges. This is an edge, this is an edge, this is an edge, this is an edge. For example, this could be, this is Sofia, and this is Burgas, and that upper thing is Varna, and etc., etc., etc. And this is Pernik, for example. Whatever, doesn't matter. This is some type of graph. The road system in our country is a graph, and everything that has connections between its elements, any set which has connections between its elements, can be represented as a graph. Okay, enough of that. So trees are types of graphs. Networks are types of graphs. We'll say what's a network and what's a tree now. So tree-like data structures, and these maybe are not that tree-like. This thing is a graph, actually. This thing is a tree over here. A tree is, for example, the hierarchy of your bosses and co-workers and etc. The hierarchy in a firm, in a company. You have a project manager at the top. He is the parent. He is the big boss. Then you have some team leaders. Each team leader has some developers under his control. You have a designer, which has nobody under his control, theoretically at least. And you have a QA team leader, which has some testers at his control. That's a tree. Okay. This thing down here is a graph. Why is it a graph? Well, because you have connections between elements. You have loops. This is a this thing over here is a loop. This is a loop. This is a loop. This is a loop. This also is a loop. Any number of vertices through which you can pass through multiple paths, we will say what the path is later, is a graph. So is a loop, and each graph, each tree which has a loop is a graph. That's a little bit to terminologies. Okay, so what is different? What differs a graph from a network? Well, a network has only one connection from one place to another. For example, not from one place to another, but only one direct connection from 2 vertices. At most one connection, at most one direct connection between 2 vertices. Meaning that your computers are wired up in a local area network. And your computers have exactly one connection with the router, for example, or the switch or whatever. And you can't have 3 roads from here to here. That's a network. Okay. You could have, but that's a more complex network. So network and graph are basically, well, almost mean the same thing. Generally, a graph is something which has more connections, but we'll generally refer to a graph as anything of these two, either this or this. It's not that important. Okay, so more about trees. We'll discuss graphs a little bit later on. So, what's a node, what's an edge? I spoke these things 100 times already. What are roots, parents, leaves? What's a binary and a balanced search tree? Okay, so some terminology. What is height? Height of a tree is the distance from its root to its furthest leaf. As we said, these are leaves. This is a leaf, this is a leaf, this is a leaf. If there were another connection over here, and this would also be a leaf, the height isn't 1, because this is 1. The height is the distance to the furthest leaf. The furthest leaf is, for example, this one. If we had another connection over here, this would be the furthest leaf, and the height would be 4 in this case, because the distance from here to here is 4. Okay, so these things are depths. This is the first depth, this is the second depth, and this is the third depth. Again, if we had one more connection at the bottom, we would have a fourth depth. And the root is always depth 0. Just take that as proof. Okay, so we said each of these things are called nodes. Nodes. These are nodes. This is a node, this is a node, this is a node, this, and this, etc. An edge is this. This thing is an edge, this thing is an edge. Each of the connections are edges. These things are edges. The root, we already said that this thing is the root. And a child is anything, one connection from its parent, because the root is a parent to everyone, the parent to a parent or grandparent to everyone. For example, this is your great-great-great-grandmother. Okay, not that great. Your great-grandmother. This is your grandmother. This is your mother. And this is you, for example. So that's your grandmother is a parent to your great-grandmother is a parent to your grandmother, and your grandmother is a parent to your mother, and your mother is a child of your grandmother. I'm telling you things you already know. So that's how terminology is related in graphs. Basically, you can imagine it as a parent-child relationship. So, what's a predecessor, an ancestor? Well, ancestor means the same thing in this context, means the same thing as child, as parent. So, parent and ancestor mean the same things in this context. We'll use them in other contexts later on. In graphs, they will mean a little bit different thing. A descendant is the same thing that a child is. A descendant is someone which descends from his ancestor. So, a successor, all of these things basically mean the same thing. A successor is a child. You can imagine it as a child in this case. Basically, this is the terminology, parent, no, not parent, ancestor, descendant, predecessor, and successor. This is a terminology we will use in traversals, but for traversals, we'll speak later on about, not for. Okay, so something else important, siblings. Siblings means brothers or sisters or whatever. So these things, everything at the same depth are siblings. These things are siblings because they're at the same depth. Because your grandmother has 2 other sisters, for example, and your mother has 1 sister. And you are alone forever. Okay, so that's basically the terminology of how to construct a tree and how to name a tree. Not how to construct, how to name a tree. Now, binary tree. Well, I told you what the binary tree is. A binary tree, defined in another way, is a tree in which each subtree, this thing, is called a subtree. And this thing is also called a subtree. And this thing can also be called a subtree, although it has only one element. It's still a subtree. Each subtree has only two children. Each node has only two children and only one ancestor or parent. So this thing has only two children. And this thing has only two children. And this thing has also only two children. Okay, each node at most two children. That's the root, that's the left subtree, that's its right child, and the root of the right subtree. And that's the right child of the right child. Okay, and that's the left child, whatever. Binary search trees. What the binary search tree is? Well, you can imagine a binary search tree like this. You have a root, and in the root you have a number. For example, give me a number. Anyone?
9.
And 9 was louder. Okay, so here's 9. Give me another number. Okay, and another number.
0.
7 sounds better than 0. So 13 is here, and 7 is here, because 7 is a lucky number. So what we have here, the left child of, we call this one a left, and this one a right child, because it's on the left, obviously. So the left and right child, the left child is always smaller than the root, than its parent, and the right child is always greater or equal to its parent. So if you told me 9, I would put it over here. But that's still a question of implementation. That's not really obligatory. Okay, and if you give me more numbers, they will be placed in the same way. For example, if you tell me 1, I will place it here. If you tell me 3, well, not pretty sure where I'll place it right now, but if you tell me 8, I will place it here. For example, this is a binary tree. Not an ideally balanced binary tree, but still a binary tree. How to create an ideally balanced binary tree, that's a hard topic. We won't discuss it. Okay. As we said, they can be balanced, and being balanced means that they will have at most a logarithm with base 2 of the number of vertices. Meaning that if you have 10 numbers and you want to order them in a binary search tree, that's how much levels, how much depths? 4 depths, yeah. Because 10 is smaller than 2 at the power of 4. Okay. And this thing is the truth that almost each level has the same number of nodes. Each node has, I'm lying to you, the number of, what am I saying? Each subtree has an equal number of nodes to the nodes of its sibling subtree, meaning that in this tree, this subtree has the same number of nodes as this subtree, or nearly the same, plus minus 1, for example. Okay, so this is an example of a balanced binary search tree. As you see, this subtree has 3 elements, this one has 2. Well, not perfect, but since we don't have another number, this is okay. If we have another number, it would go, for example, here. That would be a balanced search tree. Why do we need a search tree to be balanced? Because when we have a logarithm of x, where x is the number of vertices, we have a fixed speed at which we can get the position of any given number. Why is that useful? We'll see later. For example, if you have multiple requests to get the smallest number and the next smallest and the next smallest from a sequence, you could use a binary search tree, because searching in that binary search tree is very fast. Okay, exactly, it takes logarithm of n steps. For example, if you're searching the position of the number 5, which isn't here, the position of number 6, the position of number 6 would be found in exactly 2 steps. One step over here, one step over here. If you're searching in an array, it would take n steps. And here it takes only logarithm of n. Okay. Implementing trees. And implementing trees, we'll talk about not how to implement creation of a tree. We'll just say how to create the structure of a tree. Okay, so what's the definition of a tree? I told you it's a type of recursive definition which says each node is a tree, and each tree has nodes, has children. Okay, so what would a tree look like? Well, it will look like a tree node, and in each tree node we will have a value for that node and a list of children, and this list of children is a list of trees. Okay, so what is this thing? Actually, these things are pointers to the other, actually these things are pointers to the children of this node. So we have a node over here, and these things are the pointers to its children. That's how you define a tree. That's what structure and memory you need for a tree. There is, of course, another option. If you're strictly using binary trees, for example, you could use an array, and the element at index I, for example, has children at the indexes 2 times I and 2 times I plus 1 and 2 times I plus 2. But that's a rarer implementation. That's a fast implementation if you're in a hurry. Okay, so this thing, you store the value in that node. We will use trees to store some values ordered in some specific way. Okay, and these things, as I said, are a list of the children of that tree, of that node. Each node which is alone, this thing is a tree. Everything which has or has not children is a tree. This thing is also a tree, and these are two trees, and this is the parent of this tree. Okay, so each node is a tree by itself, and each node can have children. Yes?
I don't see the pointer to the parent.
You generally don't have pointers to the parents. It depends on the implementation, but you generally don't need them. If you're implementing a binary search tree, most probably you won't need it. There are algorithms for sorting, for creating binary search trees which don't need backtracking, or do the backtracking in another way. You could have an edge to the parent and a pointer to the parent, but it's not obligatory.
And the other thing, can we have a null value in the tree?
This value. If you're asking if this thing can be null, why not? It's not very good.
Because if we're using the array, for example, it's null value for array.
That's exactly why arrays are more rarely implemented. That's why trees are more rarely implemented as arrays, because you can't have a null value. You can have a null value in an array, but you have to use nullable types. Int question mark, for example. So what you contain here is basically your problem. You define what you want to contain here. Okay. Generally, if you're making a binary search tree, you don't need null values. They waste your searching time. Okay. So this is, for example, a tree, not a binary search tree, not even a binary tree. It's just a tree. And this thing has the value 7, and this is the list of children. And the list of children has pointers to its children. This is a child, this is a child, this is a child. And each of these children has a value and has other children, etc., etc., etc. This thing is null. This list of children here is null, because there are no children. Or empty, depends on what your implementation is. That doesn't matter that much. The more optimal decision is that each node which doesn't have children has a null pointer to a list, meaning that the list has a null value. The other implementation is that it has a list, but the list is empty. It depends on how you want to implement it. Both ways are fine. Both ways work. Okay. This is the tree node, and this is the value, and these are the children. We saw them before. And this is a value of type integer, and these are children with integer values. A list of integer children, but it doesn't mean it has to be integer. It can be double, float, or whatever. That's why we used this thing over here. That's why we used generics. Templates are in another language. Okay, so how do you implement a tree as a class? Well, you need some structure, some constructor, which, for example, takes a value and creates, and creates a node with that value. And the children is just a new list, or no, if we don't have any children. When you want to add a child, what do? Well, if it has a parent, for example, you can store if a tree has a parent. You can add it in the children. Why do you need to store the parent, actually? Not very sure. Whatever. This code is basically an example of how a tree which uses some information, whether there are parents, and that information could be the address of that parent, as you said. Okay, so
it's normal because sometimes you have to swap the value.
Yes, sometimes you have to swap, but there are other ways to swap if you want to. Well, it basically whether you have a link to the parent depends on whether you want to do swapping, for example, for each and every node. If you have access to the nodes all the time. If you don't want to have access to all the nodes all the time, but just to the root, you don't need an address back. Because when you start searching for a certain child, if you want to swap that child with its parent, for example, you just go to the parent. You can't reach the child before its parent. You reach the parent and you say, okay, this is the parent, and that below me is the child I'm looking for, so just swap these two values. And you don't really need the backwards link. It depends on what implementation you're wanting. So,
If you are searching for something and you are not sure which of the child is this thing you're searching, then you need to backwards.
yes, if you're not sure what you're searching for, and if you're not sure that your tree is a binary tree, a binary search tree, yes, you need backtracking. But that is something you will rarely need. You won't most probably make a tree in which you don't know which elements could be located. Because if you don't know where the elements are located, you just use an array. So this is a tree. This is basically the structure of a tree, how a tree could look like. It's not obligatory that it is just like that. Okay, so you probably saw the code already. We have actually, as you can see here, we don't have any tree structure. We just have a tree node, and each tree node is actually a tree. So yeah, you can use that as a tree. So for each tree node, what do we have? For example, we can get its children, we can add children, and things like that. Okay. In most cases, you won't need to implement trees. You could, but it's not very obligatory. How do you construct a tree class? Well, you have a tree class. In it, you have a root, and everything else is relative to that root. That root has connections to its children, those children to their children, etc., etc., etc. So yeah, in a tree class, you will most probably have a get root property, and not much more than that. It's yes. What? Oh yeah, the height of the tree, for example, which is not very obligatory, but yeah, that's a good idea. In a tree, you could have the height. You could have some variable which stores information whether the tree is binary, trinary, quadrinary, or etc. But in most cases, you will need this type of structure. Okay. So yeah, this is some constructor for building trees. You get a tree, and you build a tree with giving a number of trees, as you see. Oops, again that button. You have params. Params means you can put any number of trees here. So construct a tree from other trees. Basically, that's what this class could be useful for. Okay, so having this class, how can we construct a tree, which looks like this? Well, we say, create me a tree. This tree will be a new tree of integers, and this will have its first value 7, the root value of 7, and in it a tree which has a root value of 19, and in it a tree which has a root value of 1, and in it a tree which has a root value of 12, of 31, etc. Okay. And when you do that, what will happen? Well, root value of 7, this thing. Then, a new tree with a root value of 19, this tree, and in it, other trees with root values of 1, 12, and 31. 1, 12, and 31. Same thing for the next tree. For the next tree which has just 21 in it. Same thing for the tree which has a value of 14 at the root, and the values of 23 and 6 for its leaves. Basically, as I said, each node is also a tree. It doesn't matter whether you represent a tree as nodes, a tree with nodes, or just a node, or whatever. It depends on what you want to get. And you will most likely construct your trees when you start using them for things you are sure you want. For example, if you want to always have the height of the tree because you will check it often, well, okay, you'll make a constructor which, when generating the tree, calculates its height and stores it in a property, for example. Okay. How do we traverse trees? Two methods. The same methods go for traversing graphs and for traversing networks. As we said, graphs and networks are basically the same thing. Okay, so what you do, the algorithm, there are other traversals, but the two algorithms for traversing are these. Depth first search. You've implemented that in one of your homeworks, I think, and perhaps in other cases. So, what does depth first search do? Well, if you have a tree like this, and have some children in this tree, and they have other children, what does depth first search do? Well, goes to the first child, goes to its first child, and when it reaches no more children, goes back over here, and then visits the next child. Goes, for example, to this child, no more children here, go back. Okay, that's not a very good example of depth first search because it will look, no, it doesn't look like breadth first search. Okay, then we'll return from here to here, and then we'll go from here again to here, and then return as far as it can until it reaches something with a child, with an unused child. So it reaches the root again and sees that there is one more unused child, and it will go like this. That's its last step, and it will finish here. That's its last visited vertex. That's depth first search. How do we implement it? Well, basically recursively. For each node, visit its children. For each child in the node, visit the child. And when you implement that, for each, if your traversing function is called DFS, for example, what it will contain for each child in this dot children or TreeNode dot children, DFS of child. And that's an implementation of DFS, depth first search. You try to go in depth as possible. Visit always the first free child, and go from that on and that on and that on. Okay, breadth first search. Visit the first vertices first, the nearest vertices first, then their nearest vertices, then theirs and theirs and theirs. Actually, that's some type of wave visiting. If you start a wave through the graph, that wave will first reach the first neighbors, then will, not the graph but the tree, its first children, then will reach the second depth of children, then the third depth of children, and so on and so on. Okay, so that you use a queue. Okay, So, how does DFS work? That's actually what I told you. For each child of node, that's pseudocode, not what you should write in C#. It won't compile like that. But you know how to write that. So, for each child, visit that child. And how does that thing look like? First, we have 7 in our stacks, in our recursion stack. Then we go to 19. And then the first child of 19 is 1. And there are no more children of 19. So we go back to 19. Because we have 19 in our stack, the last visited. Then from 19 we go to 12. Because it's the first child. And 12 is the last member in the stack. And we don't have any more children, so we pop out 12. Then we go to 31. Pop out 31. Pop out 19. Then go from 7 to 21. Then pop out 21. Then 14, 23, back to 14 again, 6, and that's it. Pop out 6 at the last step. And eventually pop out 7 until you pop out all your stack. So that's basically the output. How we visited it. 1, 12, 31, then 19, 21, then 7, and things like that. Okay, so that's one type of traversal with DFS. BFS, breadth first search. Searching in breadth, searching in white, or whatever. Okay, so visit all the neighbor nodes, so visit all of these first, then all of these. How does that work? You have a queue of things you have to visit. At the first step, your thing you have to visit is the first node. Then, for each of the nodes in your queue, visit their neighbors. So, add these to the queue. And then for each of these, add their neighbors to the queue. So, this is how it looks like. For 7, add all its neighbors. These 3, 19, 21, 14. Then, for 19, add all of his. Yeah, you take 7 out because you've used it already. 1, 12, 31. Then, for 19, you don't need anymore. You've used it fully. 21, it doesn't have any children. Use that too. 14, well, you have 2 children to use. That's 23 and 6. And then you say that you've already used 14. And you're left with a queue of 1, 12, 31, 23, and 6. And you pop them out sequentially. And when the queue is empty, you finished your traversal. Okay. So, depth first searching in trees is done in several ways. There are several definitions for depth first search in trees. The first one is pre-order, meaning that you visit first the root. The root will be the first one popped out. Then you will visit the left neighbor. Then you will visit the right neighbor. The in-order traversal is the traversal in which you have the root, each root, for example, this one is a root 2, visited between its 2 neighbors. So visit first this, and then this. And for this will be visit this, then actually visit this, then this, then these. That's an in-order depth first search traversal. The post order is visit first its 2 children, then visit the node itself. Okay, these things you won't probably need them soon. You could need them in about 2 or 3 months, but this is something that is not very easy to understand. Okay, so what do you do? What happens if you use stack instead of a queue in breadth first search? You probably already saw the answer, but what you do, well, when you use a stack for a breadth first search, meaning that the first thing popped out will be the last thing pushed in, well, that means that you will have actually a depth first search. If you do a breadth first search with a stack, it's actually a depth first search. So that's how you implement depth first search with a stack, without recursion, I mean. You just use a stack. You write a breadth first search, and you just change the data structure from queue to stack. You get depth first search. The other way around, you will get breadth first search. Okay. So, traversal over tree. We should have some demo over here. Trees. What do we have in trees? We have some class which defines the tree. That's just a naked constructor in our TreeNode class. And we have probably a main method, or we don't have a main method. Yes, we have a main method somewhere. So, here is our gigantic class, which consists of the TreeNode, which we showed you earlier, and it has a list of children and a value, and a value which has whether it has a parent. I'm not sure what that's used for. You probably not need it. Anyway, that doesn't matter. Oh yeah, that's used for whether it has a parent if you want to add another parent to it. That's because if a child has two parents, you get a graph, not a tree. Because if you have, for example, this is a tree, and these are some children, and for example you say that this thing over here has this thing as a parent, okay, but if it has this thing as a parent also, first it doesn't sound logical your sister to be your parent also, and then it destroys our tree. It's no longer a tree. This thing has a loop, this thing is a loop, from here to here it's a loop, and when you have a loop it's not a tree, it's a graph. Okay, so the has parent boolean variable works only to warn us when we're trying to add more parents to a node than it could possibly have. Okay, so the tree structure class, actually, what does it have? Well, it has a tree node, which is a root, and it has some algorithms, and these algorithms are traversed with DFS and traversed with BFS. And we saw how these things should be implemented. That's a BFS. We have a queue. You add the first node, the root, and queue that. And then, while your queue isn't empty, you try to push in the next node to visit. The next node to visit is the child node. Each and every child node. And, for example, you print them. If you traverse it with the DFS, what will we have? Well, a stack, same construction as here. Absolutely the same. Only that this thing is a queue here, at BFS queue, DFS stack. That's the only thing you need to remember. And DFS with the stack is a better idea than DFS with recursion, because recursion could fill up your program stack and crash your program if your tree is larger. So when you do it with the stack, it will probably be even faster, because you don't have the recursion. When you can avoid recursion, avoid it when it's possible. Okay, so we have some main method. We construct the tree. We saw how we do that, and then a traversal with the DFS, a traversal with the BFS. We have the tree as in the examples, I think. Yeah, 7 at the top, 19 as a child, then 21 and 14 as children. Yeah, exactly the same example as from the presentation. Okay, so let's see how this thing works. Depth first search traversal, and that's a recursive traversal, meaning that we can analyze when we've went one level down. That's why we have this tabulation over here. So from 7 we visited 19, then we visited 1, 12 and 31, then we visited 21, then we visited 14, and for 14 we visited 23 and 6. This is pre-ordered traversal. First the root, then the children. Okay, so breadth first search with queue. You don't have any idea which are children and what is what. We have 7, then we visited all of 7's neighbors, 19, 21 and 14. Then we visited all of their neighbors, and that should be 1, 12, 31. 21 doesn't have neighbors, and then 23 and 26. And depth first search again, but this time with the stack, not with recursion. We have no idea where it's going down the tree, so we don't have these tabulations as in before. Actually, what happens here? Well, each time the recursion is called, one tabulation is added to the printing. Okay. So, in this thing here, we just have a stack. We don't know when which came in, so we just print them out. Okay. So that's basically some traversals. You should remember them. These traversals are good for graphs also. You have a question?
Yeah, I have a question. How did we implement post-order search?
Post-order search, not pretty sure. What? Not exactly. It's just a matter of how and when you pop things out of your stack. It's still how you pop things into your stack and how you pop them out. Not a matter of going back actually. Post order meaning that you have all your that should be a BFS in which your output you put it in a stack, I think. Yeah, BFS with recursion. Actually, if you do your BFS traversal and you put things in a queue, when the time comes to pop those things out of the queue, order them in a stack and then pop them out when you finished with popping out from the queue, and that would actually reverse the order of visiting. That would mean that actually post-order traversal, I think, I'm not sure, is just a reverse of pre-order traversal, meaning outputting things in backwards. So if you output things from pre-order traversal backwards, you will get post-order traversal. So traversals are mainly a matter of how you output your results. So think of it, for now, think of it as that, how you output your results. If you output them backwards for a BFS, you will get post order. Not pretty sure, but I think that's the idea. Okay. Yeah, you should get exactly that. If you write it through, you will see. Okay. So, going through the presentation. Balanced search trees. You want a break? Yeah. Votes for break? Okay. 10 minutes from now on. And I'll interrupt the recording. Okay, so balanced search trees. What are balanced search trees? We saw what a search tree is, a binary search tree. A tree in which all the elements that are smaller than the root are at the left child, and where all the elements that are larger than or equal to the root are on the right part of that tree, meaning at the right children. Okay, so we'll speak about some of those balanced search trees. We'll say which are fast, which are not that fast. We'll discuss what a B tree is. It's a more hardware dependent tree, hardware optimized actually. So yeah, ordered binary trees, I said that 1,000 times already. So okay, smaller than or equal to the root are at the left, larger than the root are on the right. Previously I said larger than or equal to and smaller than. That doesn't really matter that much. So okay, they say that standard implementation is that when you have tree, if you have, for example, 7 here, if you have another 7, it will be here. And everything smaller than that will be at this side. And here you will have 8, for example. So that's a binary search tree. It could be the other way around, meaning that there is a possibility that 7 is on the right, but 8 will certainly be on the right, most certainly be on the right. Okay, so balanced tree. A balanced tree is something which has basically a logarithm of the tree's number of maximum number of neighbors at each vertex. Okay, that's a complicated formulation. If you have a binary tree, its height will the property of balanced trees is that the height of a binary search tree, for example, is of a balanced binary tree is exactly logarithm of the number of vertices at base 2, meaning that for 16 for a number of vertices which is 16, the height will be 4. For a trinary tree or a quadrinary tree or a, I don't know what the word is for 5, and etc., the base is corresponding to the number of children for each node. So for a binary tree it's 2 children, for a trinary tree it's 3 children. So a balanced trinary tree would be with a base of 3, logarithm with a base of 3 of the number of vertices, and so on. Trinary and quadrinary trees aren't used. So what mostly trees are used in the binary meaning, only binary trees. They are the only effective ones, or at least up until now. Okay, so I said that they have a height of logarithm of n with a base of 2, and searching, of course, costs that amount of comparisons. So when you're searching for something in a binary tree, you need exactly that much comparisons. Something binary trees are used for searching for a lion in a desert. That's the Bulgarian equivalent. I'm not sure how to translate it in English. When you have the option of only asking where is the lion and getting the answer, what do? You do is the lion here? And for example, the answer is no. Then is the lion here? And no, for example. Then is the lion here and here and here, etc. And you narrow down the searching part and then reach the lion, for example. That's how that's a binary search, and the binary search tree can do that. Actually, what I did here is something called binary space partitioning. Here people working with 3D graphics should listen. So binary space partitioning is dividing your entire volume, entire area in which your 3D objects are, dividing them into boxes. First box is the entire area, then another box meaning half the area, and then half the area, and then half the area, and that creates fast searches, but that's another subject. Just so you know that there's such a thing. And that's an optimization. Okay. So this is a binary balanced search tree. We have a lot of elements. I don't know how much there are. Actually, I'll calculate how much they are. All the levels are full. This is a full level. This is a full level, and this is a full level. And of course, this is a full level. So this is height 4. So 2 at the power of 4 is 16. So this should be exactly 16 elements. 3 here, 6. 3 here, 9. And 6 and 6. Okay, didn't calculate it pretty much right. Should be 15, yes. Should be 2 at the power of 4 minus 1. So this should be 15 because of this note over here. Whatever, that doesn't matter that much. What is important in a binary search tree, the definition, is that each subtree at an equal depth, these are subtrees at an equal depth, and these are subtrees at an equal depth, have the same number of vertices in them, the same number of nodes in them, or whatever you like to call them, the same number of these things in them. So, or the same number plus minus 1 at maximum. Okay, so this is an optimal search tree. When you're looking for example, the number 37, you get to this node. You say, I'm looking for 37. The node at which I'm in has a value of 33, so I have to go in the right subtree because I'm searching for something higher. So I go here. 54. 37 is lower than 54, so go left. Then 42. 37 is less than 42, then go left again. That's a binary search in a binary search tree, and it's very fast. Instead of searching through 16 elements, in the worst case, we have searching through 4 elements, in the worst case. So 16 and 4 isn't exactly a pretty describing example, but an example with, for example, 1 million entries, 1 million nodes. If you have an array and you have to search in an array, the worst case scenario is that the element you're searching for is last, for example. So you start from the beginning, you go through 1 million elements. If it's sorted, if it's a sorted array. Yeah, the binary tree is also sorted. If you construct a binary tree, that's the idea. So if you construct a binary tree or sort the thing and search binary, it's basically the same idea as the colleague said. If you search 1 million elements stored in a binary search tree, that will take how much? 20 steps compared to 1 million. That's a lot. So that's a big difference. So that's what binary search trees are good for. And they take up the same amount of space. Okay, a little more if you have connections and pointers to the next node. But if you store them in an array, it's the same thing. Okay, so balancing binary search trees is very hard. It's difficult to write an algorithm which does this effectively. First does this and then does this effectively. There's a difference between these two things. It's easy to make a balanced search tree if you do it with a stupid algorithm. You can always do try this option, then try this option, then try this option, and that will take a lot of time. Binary search trees have to be fast in reordering themselves. If you remove an element, reordering the binary tree has to be fast, so that the data structure is still fast. Because binary search trees are often used for insertion and removal. So there are several implementations of balanced binary search trees. First are AVO trees. Now I'm not going to tell you what the abbreviation means because I'm not sure either. But if you Google this, you'll get an idea. So these things are perfectly balanced. They always implement this case. They always have this case. Or in the worst case, this element is not here, for example. One element is not there at the bottom. They are ideally balanced like this one here. And implementing this algorithm is more complex. And I think the algorithm itself is slower. So ordering an AVO tree is slower than, for example, ordering a red-black tree. But I'm not pretty sure. You have to check that. In any case, it's too complex. It's really complex to implement. Yeah, and are there is there any information on how fast balancing is? You could check that. So, while the colleague checks that, you could go through yeah, 2 times logarithm n, and red-black trees I think balance in logarithm of n time, if you can check that. So AVL trees have the most complex algorithm to balance, but they balance ideally. Red-black trees, if you have to implement something, you implement a red-black tree. Red-black trees, they're still hard to implement, and they're not very optimally balanced, but it seems that most of the binary search trees implementations are based on red-black trees. So, what's a red-black tree? It's not very important to know. It uses terminology from roulette, if you're interested. What? Yeah. So exact. AVO trees, more complex algorithm, harder to write, harder to execute by the computer. The colleague said that this is 2 times logarithm of n, where n is the number of vertices. 2 times logarithm of n for AVO tree, for an AVO tree, to balance it. Meaning that if we have if we have frequent insertions and deletions in an AVO tree, it will be slow, because it takes 2 times log n. And red-black trees take only log n for reordering, only log n. So basically, red-black trees are twice faster at reordering and a little bit slower at giving you the smallest or largest element or some element. Why? Well, because this thing is a little less balanced. But a little less balanced, that could mean, for example, for every 1 million elements, the red-black tree will give you a logarithm 20-step search, and a red-black tree, an AVL tree will give you a 20-step search, and a red-black tree, for example, a 25-step search, which isn't that big of a deal. 20 isn't that smaller than 25, and the excess computation cost of reordering the tree at the AVL trees actually make them not that very good as red-black trees at storing information. So most implementations of trees are red-black trees, most of them. Okay, AA trees, they say that they're relatively simple to implement. They are probably pretty rough balanced. They're probably not even well balanced at all. They're some type of tree. You could check them out. If you have to implement a tree, well, you could try to implement an AA tree. But you have to check it out. So find, insert, delete, logarithm of n for AVL trees, 2 times logarithm of n. At least that's what information we got here. If you have a question?
What means row bounds? That there are no
That they're not ideal like this. This is ideally balanced, roughly balanced. Well, there could be, for example, this thing could be missing, and this thing could be 1 level higher, one depth higher. It would have a higher height, and a roughly balanced tree is a tree which doesn't have an optimal height, meaning that some elements are missing from here, they're somewhere else, or something like that. So this is ideally balanced, and not ideally balanced is, for example, having this thing, or for example this 59 not being here but being here. That's not well balanced, I think. What? It's bigger than what? Oh yeah, it's bigger than 54. Okay, so I can't give you a good example of
The good example is after 54 we have 59, then 60, and then 51.
yeah, okay, this is, yeah, the colleague is right, this is a good example. 59 is not here, but it's here. This is a not very well balanced binary search tree. It's still relatively well balanced, but not very well. So red-black trees, you could expect something like that from them, or some type of ordering in wellness. So most of the find operation everywhere takes logarithm of n steps. As the colleague said, AVL trees a little slower. So 2 times logarithm of n still isn't that big. So logarithm of 1 million is 20. Yeah, for inserting and deleting only. So AVL. Yes. So AVL, insert delete for AVL is 2 times log n, which for 1 million elements is 40 steps, for example. And searching in a red-black tree, for example, could be not 20 but 22 or 23 steps. So basically you decide whether you need an AVL tree or a red-black tree. But the most common case is an AVL tree, yes?
Well, you said that we can put the value from the tree in array. What's the
in
point
what?
In array. We can
Yes.
put the value
Yes.
the tree in array. What's the point of using a tree when we can use array?
The point of using a tree, a multitude of elements of objects which have links to each other, instead of using a normal array like this. The point is that when you start resizing, if the tree has a lot of insertion operations or a lot of deletion operations, what happens is that if you have to insert in an array, what do? You reallocate the array in a new place, which takes a lot of time. When you have to insert in a list of things, you just say that this thing does no longer point to here, no longer points to here, but points to this element here, and this element points to this one. So yeah, that's constant. That's a constant time loss, and this is a time loss multiplied by the number of things you have in the array. So with an array, insertion, when the array is too small, is much slower. Or you use up a lot of memory if you want to be sure that you have enough storage for all your elements. So yeah, that's basically the downfall of representing binary trees as arrays. Okay, and other types of trees, for example, heaps can also be implemented as arrays. And heaps have some advantages when implemented as arrays and some disadvantages. The same kind of disadvantage, the good advantage that you always know where is the rightmost. Your insertion always is at the last element, the last added element. That doesn't matter that much. We're talking about B trees now. So B trees are binary trees, but binary trees with some additional properties. B trees are actually created to optimize on hardware. They're created so they take up memory optimally. The orders themselves in memory optimally. You know that memory is split into tiny sectors, which are called pages, I think. Memory. Clusters, that's for disks. I'm talking about RAM memory. Standard RAM memory is divided into pages, which is something like sectors, but in RAM.
Segments.
There are basically two types. The idea is that RAM is split up in some pieces, and B trees are optimized for storing every B tree subtrees should be able to be stored in a page, a single page. That's basically the idea. The idea is ordering the B tree, well, not exactly in a page, ordering the B tree so that it is effective to be ordered in memory by hardware. So B trees are actually optimized not only programmatically or algorithmically, but are also optimized memory-wise, hardware-wise. So they basically work faster than other trees, just not because of complexness of the algorithm, but because they're easier to address, basically, something like that. Okay, so there are some relations. Now you could try to remember this. Yes?
I imagine it's some kind of list of trees because list is allocating some space in the memory. Then for the B trees, it's also allocating some memory, and it says that all these sectors in the memory, you are going to use them for B tree, and you know how to address them fast. You don't need to search. They are next to each other, so you're just searching.
Yeah, it's something like them being ordered close to each other, but not exact. I'm not sure if that's a guarantee. Actually, if we try to decipher this stuff over here, a B tree of order D, what's order D? Some number, order. Okay, it gets complicated. Let's not try to decipher that. It's just faster. You could Google it, you could try it on Wikipedia. You're not really obliged to know that. You're obliged to know that if you want to implement something very fast. But that would probably mean not writing in C#. Because writing in C# makes things that are not that fast. So yeah, you have an order D of a B tree, and that order D has between 2 multiplied by D, and between D and 2 multiplied by D keys range from D plus 1 and 2 times D plus 1. Okay, this is a little conceptually hard to explain, understand even harder. Again, keys in each node are ordered increasingly. This is not basically a binary tree, but something like that. Something used for fast searching. Again, they take logarithm of n steps, and yeah, efficiently stored on disk and on memory, I think. not really important to know what exactly this sentence over here means.
That means that when you create this kind of tree, you can already allocate memory for all the channels.
Not exactly meaning that you have already allocated the memory. This is a specific type of ordering in which you have some keys, and these keys follow this rule that each is between d plus 1 and 2 times d plus 1. And they have some theoretically proven advantages over other trees thanks to this characteristic. But it's not really important to use up your memory for that. Use it for other things. Use it for this. What's a red-black tree, for example? That's something that is useful to remember. Okay, so yeah, B tree, not exactly a binary tree. Something like a binary tree. Yeah, and as they said, 2, 3, 4 tree. That's how you get elements ordered in that, and I think this thing is basically optimal for memory storage. Can't prove to you right now why, but you could take my word. Yeah, really, I'm not really sure how to prove that this thing is optimal and how exactly it works.
It looks like that you have 3 different options.
Yeah, you have. Yeah, but that's not the reason that it's optimal for memory. Because of the sorting, because of the way that values are sorted, meaning that, for example, you have this 1721 thing, and I think the order is this thing 3 over here. So the order of a tree is the number of children it has at each node. So order of a binary tree should be 2, I think. And this tree could have, as you see here, more than 1 address remaining. I think it could have 2 or 3 addresses here. I'm probably going to lie to you about this one. So you should probably check it out. Last time I tried to explain something of the sort, I explained an index tree instead of a heap. So I'm not going to try again. You should check it out in Wikipedia. You will most probably not need it. So check it out so you know what it is. Not really necessary to remember it. You won't. The probability that you use it is very low. It's used for higher optimizations. So, what's more important? You should know what these things, sorted dictionary and ordered set, are. So, sorted dictionary, you know what a dictionary is. We're going actually to talk about it in the next lecture. A sorted dictionary is a type of dictionary based on a red-black tree, and the values in that sorted dictionary are sorted by key. So insertion and removal actually means reordering that dictionary, and that reordering is achieved through a red-black tree reordering. That's why actually the dictionary itself is implemented by a red-black tree. And it works like a standard dictionary. You tell it, give me the value at the key, for example, A, and it gives you something. Works like a standard dictionary, but keeps its elements ordered by key in memory. Ordered set, well, a set in which you have elements, and a set is fast at insertion at a given position. If you know where you're going to insert, you could use an ordered set because it's fast. An ordered set is again a red-black tree, ordered in some way, and when you tell it give me the first element, it knows which the first element, for example, the smallest or the largest is, and it's very fast when you want to insert at a given position. If you know which position you have, in which position you have to insert, use an ordered set instead of a normal data structure. These things obviously aren't enough to implement a balanced binary tree. So this is a balanced binary tree, but it's not the best way to implement it using a dictionary or a set for that matter. That's why there are a lot of external libraries, especially for .NET, the Intellect power collections. That's what's most used, and that's an example of how to implement abstract data types and how to write your code for these abstract data types. Many programmers write abstract data types in which, for example, properties, there are no properties, there are something like classes in which variable names are 1 character long. And that's not a very good example of quality code, but many programmers do it. Intellect power collections, as much as I've seen, have relatively good quality code. So Intellect power collections, that's what we recommend to use. Of course, there are other libraries. And these things are very flexible. They are created so they are specifically used with C#, specifically for these purposes. And there are a lot of things here, from bags, ordered bag, whatever that is, from heaps to binary trees, etc., etc., etc. Okay. So that's the address. You can check them out. You can download them and use them. powercollections.codebase.com. If they're not there, just Google power collections Intellect and you'll get them. Okay, so talked about trees enough. Now to mention a little about graphs. How many slides do we have first? We have 20 slides left. Okay, let's, how many time are we recording? Oh, 28 minutes, no breaks. I was going to give you a break, but 28 minutes is too short for a break. Okay, so graphs. Now forget about the trees for a minute and try thinking of connections like this one. This is a graph. Although it looks like a broken glass and something Picasso made, perhaps, it's called a graph. You have some connections between some things. And these connections could have values, could not have values. We'll see them in a moment. So, trees, we said, some nodes in which each child has only one parent. One child can have many parents, but each child has only one parent. In graphs, that thing isn't applied. In graphs, there are nodes, and you could say they have parents, but they have more than one parent. Meaning that you can get from one place, for example, from here to here, in a lot of ways. In a tree, you can't do that. In a tree, if you want to get from one place to another place, you have exactly one route through which you can go. In a graph, things aren't like that. In a graph, you can go from here to here, through here, through here, through here also, or here, and etc. There are a lot of ways. Anything in which there are two, yes?
Then why are those arrows?
We'll speak about the arrows later. Arrows mean directed paths. That's why I went from here to here, through this arrow. The arrow means the direction in which you can go. But we'll discuss that in a moment. So, of what? Oh yeah, that thing. This thing is called a loop or a knot or something like that, and it has no idea. It's like just having a connection to yourself. For example, you can go from the city of Sofia to the city of Sofia again, but not traveling through the center, but traveling around Sofia. And that way you avoid traffic, for example. Still, you go from Sofia to Sofia, right? But you're going through a road. That's how you can imagine it. It basically has no real implementation idea. It just says that such a thing is possible. It's not forbidden, it's possible. But if you search for a route from one place to another place, you will probably not use that, because it's pointless. It only makes your route longer. Okay, so what we said, each node, multiple predecessors, multiple successors. That's why they're called predecessors and successors, not parents and children, because one child can have 7 parents. That sounds a little unlogical. Okay, so somebody asked what those arrows are. Arrows mean a directed connection. Normally you would see a graph in one or two ways. One way is have it like this, with no arrows. For example, this is a graph. This is called an undirected graph. You can go from here to here, whoops, and from here to here. You can travel in both directions. In this type of graph, which you see here, that's the other type of graph, it's called a directed graph. And a directed graph, well, you can't reach 11. You can go only from 11 to somewhere, but you can't go from 4 to 11, for example. Yeah, that's a one-way street. An unordered graph, like this one, has two-way streets. You can go in one way, you can go in another way. And a directed graph has one-way streets. This is a one-way street. It's a violation to go from 4 to 1. But it's okay to go from 11 to 4. Okay. There are other characteristics of graphs. For example, there is a weighted and an unweighted graph, but we'll talk about them in a moment. So yeah. Yes, I'm interested. What? Meaning having some, oops.
Basically, you have charts of parents, doesn't matter, and different pointers to different charts of parents, you have different priorities.
Meaning that you have a value 2 here, a value 4 here, and something like that. Yeah, so priority is basically a value. Can you have priorities? Well, yes, and this is called a weighted graph. A graph which has weights. Priorities or weights or whatever you call them, or lengths of the roads, for example, kilometers from Sofia to Pernik and to Plovdiv and to Varna, etc., etc., etc. Those are weights. We call them weights. And we call a graph with weights a weighted graph. And this graph over here is an unweighted graph. Weight like this. I'm not sure if I'm pronouncing it right. This type of weight, not weight as in worldwide weight. This type of weight, meaning how heavy this transition is from 4 to 1, or how long or how expensive or whatever you like to call it. Something I was going to say, but I forgot it. Okay, I'll say it later when I remember. So, each node could have multiple predecessors. This node has multiple successors over here, meaning that 21 and 14 are all successors of 7. And yeah, that's what a node is. The same thing as in a tree, but we said that each tree node is a tree by itself. Well, each graph node is a graph by itself. So trees and graphs, they're basically the same term. This thing, the entire thing, is called a tree. Because there is only one way to go from A to B and from B to A. And that's the road AB. If we had this, actually not this, but if we had C as an element here, and like this is not a tree. But if we didn't have this connection, this is a tree. Okay, that's the idea. So, a node, one element of the graph, or a vertex. So, can have a name, a value, and whatever you like it to have, same way as the tree can have, and probably can keep a list of adjacent nodes. That's not obligatory. There are different representations of graphs. Some use lists of adjacent nodes for each node, some don't. An edge. What's an edge? An edge is this thing. The connection between A and B. That edge can be directed. So that means that that can be a one-way street from A to B. It could be undirected, as it is now. It could be weighted, meaning that it could have a value of 4, meaning that there are 4 kilometers from A to B, for example. Or going from A to B costs $5 or something like that. That's how Google Maps works, by the way. It has a network of cities, and from each city to each city there's kilometers and there's taxes and etc, etc, etc. And if you click from Bulgaria to Romania, it will say the kilometers are some number. Then there are taxes on these routes at each and every point, and these taxes have these values. And if you, and it says use caution, fees may apply, use caution, it may be snowy. All these things are kept in a graph. What? Yeah, that can also be stored. That can also be stored for an edge. So yeah, same way as you can store everything for a node, the same way you can store everything for an edge. But the basic idea is that an edge is something which connects two nodes. Okay, and could have a name, a value, and everything else you want. Nodes, edges. Okay, directed graph. I told you what a directed graph is. A directed graph is something with directions. This graph, by the way, this entire thing, is also an unconnected graph. Unconnected graph means that there are 2 points, 2 cities in this graph from which you can go from one to another. There exist such places. From one to the other or in the opposite direction. This is an unconnected graph. Why? Well, because this one is out. You can't reach this by any means. You can't even violate the transportation rules to reach that place. Okay, so basically you have to swim here. If you imagine these as islands with bridges, everything which is a lonely island, which reminds me of some songs, everything which is a lonely island is called an unconnected part of the graph, and this entire thing, the number of if the number of islands, of unconnected islands, is more than 1, then we have an unconnected graph. So what we have to mention here, edges having direction, that means an ordered graph. So having not ordered but directed graph. Some directions. You can't go from 1 to 3. You can go from 3 to 1, but not from 1 to 3. Okay. Undirected graph, you can go from anywhere to anywhere as long as there is a connection. For example, here you can go from A to D and from D to A. That reminds me that actually an undirected graph is just a directed graph with an edge like this and an edge like this. Two-way edges. So yeah, an undirected graph is basically a directed graph with each of the edges pointing in both ways. So having 2 edges between 2 nodes in the graph, which point in opposite directions. You could implement it with pointers, but that's a rare implementation. Generally, yeah, you could implement it with pointers. Generally, how you represent a graph? Okay, how you represent a graph is the most common representation is a list of neighbors. Each node has a list of neighbors to which you can go. For example, the list of neighbors for F is A, D, G, and J. That's the list for F. It's good for some ideas, it's bad for other ideas. For traversal through all the elements, it's generally quicker. There are other representations, for example, a matrix of adjacency. We'll talk about this in a moment. Let's just say what a weighted graph is. We already mentioned the weighted graph is this. You have an edge and you have a value for that edge. For example, from Aktopol to a city with F in Bulgaria from Aktopol to Filipovci, it's 10 kilometers. Yeah, right. In another lifetime, it takes 10 hours. For example, this could be time. This could be anything. There's no way to reach Q. Q is no town in Bulgaria. That's why there's no way to reach it. What? Yeah, it's not a valid diagram. Okay, there's okay, don't know what Q is. There's no way to reach E and C, and that this graph consists. This is a, I'm not sure what the word is. This is a graph consisting of 3 graphs. So this is a graph, this is a graph, and this is a graph. Array of graphs. I think there was a word multi-graph, but I'm not sure if it means what I'm thinking. So I won't say that it's a multi-graph. So each rib, each edge or connection or whatever you like to call it has some weight. And when you travel from one place to another, you have this weight. Or this, this ability to transfer water, for example. This could be a model of a pipeline, of many pipelines, and it says that this station can transmit 10 units of water through here and 6 units of water through here, etc., etc., etc. And this is useful for the max flow algorithm. We've heard about it in the trial exam or whatever it's called. What's a path? So a path is a sequence of nodes, and these nodes should be at least 3. A path is a sequence of nodes which is at least 3 or more. So this is a path, A, B, C. And a path is something in which edges exist, meaning that if there are connections between A, B, and C, and A, B, and C are 3 vertices total, that's a path. For example, HKC, which is HKC, there are no direct connections between H and K and between K and C, and also HKG is also not a path because there is no direct connection between H and K, even though there is a connection between G and K. A path is something. A path is something intuitive. Actually, you know what a path is without me telling you. You know. This is a path, and this is not a path. For example, that's not a path. A path is something passing through vertices which are directly connected to each other. When are 2 vertices directly connected? When we have something like this, when we have an edge between them. When are they connected? Not directly, but just connected? When there's a path through them. Okay, a little more definitions. In a directed graph, same thing, but the path is directed, meaning that A, B, and C is a path. Why? Well, because this connection is valid and this connection is valid. But CBA is not a path because this transition is not valid. We can't go in backwards direction. And AGK is also not a path because we can't go from A to G. Okay. So, what's a cycle or a loop or whatever? Well, a cycle is this thing. I told you already. Going from one vertex to another, and then reaching the same. A path starting from one vertex and finishing in the same vertex, that's a cycle or a loop or whatever. What's a simple path? A simple path is a path with no cycles. So this, for example, is a simple path, but it doesn't exist actually because I didn't use proper connections. Acyclic graph, a graph with no cycles, and also a what? Yes, a tree. An acyclic graph is a tree. Okay, yeah, actually it's said down here. Okay, so 2 nodes are reachable. Yes, that's what the other term is connected, not directly connected, but just connected. If there is a path between them, and the connected graphs, each 2 vertices from it are reachable. Okay, this is a connected. That's an unconnected graph. Okay, graphs. What are their applications? Well, except for mapping and for road maps and sewage calculations, pipelines, etc., and connecting networks, and besides that, calculating the flow of electricity, for example, or anything else, they are used at social networks. How? Well, Facebook. What does Facebook do? It has a graph of your friends, and your friends also have connections between them. And when some of your friends does something, all of his neighbors, meaning you two, get notifications. And when do you receive notifications like you might know this person? Well, when you're this person, this is you, and this is your friend, and your friend is connected with somebody, and somebody else, and when do you receive, and you have some other friends, friend 2, friend 3, and for example, when does Facebook ask you if you know some person? Well, if a lot of your friends are connected with this person, then most probably Facebook will say, oh, you have a lot of acquaintances with this guy. You know, a lot of your friends know this guy. You could probably know him. Do you know him? And when you say that you know him, Facebook does this and connects this to your friends list. That's how social networks work. And not only that, but that's some example. Okay. State machines. One more thing. State machines are there's something a little more complex. You have letters. You have A, you have B, you have C, you have D, you have E, for example. Those A, B, C, D, E are states. The state A, the state B, the state C, the state D, etc. And for example, a machine is known that it can convert from state A to state C, from state C to state E, from state E to state B, and from state B to state D, for example, or something else. And from state C to state B also. That's good for operating a machine. You can simulate a machine's behavior through graphs. A machine which has states. And for example, this is my car without any ignition. This is my unignited car, A. And B is my moving car. And what do I have to do to reach B? Well, my first option is to ignite my car and, for example, put it in 3 gear. Yeah, you get my idea. Or not ignite. My first idea is to release my handbrake. Release the handbrake. You know, go through here. Release the handbrake. And then, if I'm on a hill, I'll probably start going. Probably start going down. This is my moving car. This is my not moving car, unignited. This is my unignited car with a handbrake down. The other option is don't release the handbrake, ignite the engine, put it into first gear, and then press the gas pedal, and then I'll start moving again. These are my options. So a state machine can give you an answer, what things you have to do to get from one state to another state. That's one option. They can do a lot of other things. They can process words, for example. A valid word for a word processor is a word where, for example, you have the letters W, O, R, D, E. So, what are words for our machine? For our English understanding machine? A rod is a word. Rod means that which you use to fish. So, rod, yeah, but not in this way. This thing isn't here. Okay, I'll draw it again. We have the letter W, the letter O, the letter R, the letter E, and the letter E, for example. And these things are parts of a graph. E, D, R, O are parts of a graph. So, how does a word processor realize if the word is valid? Well, the word is valid if, when going through the vertices, we have a correct connection. So, we can define our alphabet like this. The word exists in the English language, for example. We're creating a processor for the English language. And the word exists. And the word rod also exists. So we have this, like this, word, and we have also rod, R-O-D, and we have the word we. So, what? Yes, in this situation, my word processor isn't very good, and it will understand the word woro also. But we're defining some kind of word processor. You know, making the perfect word processor isn't my task here. My task is to write some word processor. So, our word processor will understand we, because we're coming from W, okay, W, and then E, okay, this path exists. Then we'll understand the word word, because we have W-O-R-D. In this condition, my state machine can understand the word W-O-R-O-D, which is not any real word in the English language, but it's still a valid word under my processor. I've defined an alphabet where this is a valid word, etc., etc., and also understands rod. But it doesn't understand wad. No, it understands wad also. It understands wad, but it doesn't understand, what doesn't it understand? It doesn't understand wheel. It doesn't understand wheel, for example. This thing can't pass. This is an example of a state machine. There are other restrictions you can give to state machines. For example, give some values at the ribs. Or say that when your state machine passes through the word, it will have a sum of 5 and 6 and 7, for example. And you can do things like that. And this is a very powerful mechanism, and you could do some further reading on it. There are things word processors, there are things state machines can do, which are very useful. Read about them, there are a lot. Okay. How do you represent a graph? Several ways. These 3 ways, there are other modifications of these ways, but these are the basic ways to represent a graph. Adjacency list, probably the most commonly met. If we have a graph 1, 2, 3, and we have a connection from 1 to 3 and from 2 to 3, and we have 4 here, and we have from 3 to 4 and 2 to 4. What would our adjacency list look like? For the vertex 1, we have the connection 3, the list of 3. This is a list. For the vertex 2, we have 3 and 4, a list of 3 and 4. And for no direct connection to 1. Only direct connections. The adjacency list means which are my neighbors. 2's neighbors are 3 and 4, or 2's friends, or whatever you call them. 3 is connected to everyone, so it has 1, 2, and 4. It's not really obligatory to sort them. I'm sorting them here, but it's not really obligatory. It doesn't matter. Okay, so 4 has a connection to 2 and 3. That's an adjacency list. And that's how you build an adjacency list. So for each of these, if you want to check if they have a connection to some other neighbor, you have to go there and go through their entire list to check, for example, if 2 is connected with 1. You have to check all of these and then decide that it isn't. Which means this is rather slow, but it's fast in other cases. So checking if 2 vertices are connected using an adjacency list is slow. And if you have to, in your program, if you have to check very often which vertices are connected to which, then adjacency list is not that potent. The other thing, which is a possibility, is a matrix of adjacency. How does our matrix of adjacency look for our same graph? For 1, 2, 3 here, and 4 here. These were connected like this. And 3 was connected to, doesn't matter. It's not the same, but whatever. Okay, so adjacency matrix 1, 2, 3, 4. 1, 2, 3, 4, and we say we have a connection. If we have a connection from 1 to 2, we say that the position 1, 2 has a 1 in it. The position 2, 1 also has a 1 in it. The position 3 to 2, 3, this is 3. The position 3 to 2 also has a 1 in it. The position 2 to 3 also has a 1 in it. This is when we're using an undirected graph. If this were a directed graph, for example, I'll make the edge 3 to 4 directed. The 3 to 4 will be, from 3 to 4, do we have a connection? Yes. But from 4 to 3, do we have a connection? No. So, everywhere where we have a connection, so 2 to 4 also has a connection, and 4 to 2 also has a connection. And I think those are all of the connections. All of the other cells are zeros, meaning that we can't go from one place to the other. And I'm not sure if I'm feeling this right, but yeah, whatever. You got the idea. That's the idea. Yeah, I know. I'm an artist. Picasso is jealous. Okay, so that's basically, so these zeros over here are non-existent. So that's a matrix of adjacency. Yes?
If it is not with an arrow, can this symmetry just make it disappear, not to make that much of a memory? You want to take these things out. Yes.
You can't make a matrix in which you don't have these members. But yeah, you could not consider them, but the memory will still be wasted. That's the bad part of a matrix of adjacency, that it always waits n times n memory. And when you're going through all of them, if you have to check if 2 is connected to 3, that's extremely fast. That's a constant speed. You only check the position 2, 3, and you see that 2, 3 is 1, and you say, yes, we have a connection. What's bad? When you have to ask how many, which are the connections of 2. And if you have 4 vertices, you have to go through 4 positions. If you have 40 vertices, you have to go through 40 positions, and if 2 has only 2 connections, you're pretty much screwed. So, yeah, matrices of adjacency are used very rarely. Very, very rarely. Mostly things like adjacency list, because when you're traversing graphs with the breadth first search and the depth first search algorithm, which are exactly the same as in trees, because trees are graphs. When you're traversing graphs, what do? Well, you use an adjacency list, because when you have to check what neighbors does one have and visit them all, you just go through first member of the list, okay, add this to the queue, add this to the queue, and etc. Okay. The other thing, a set of edges, is used again rarely. The set of edges is used in the minimal spanning tree of a graph. But what's a minimal spanning tree? I'm not sure if we're going to discuss that. A set of edges in 2D or 3D graphics. In the what? More likely representing which vertices form triangles. That could be, yes, that could be a use case for a set of edges, but it's generally not that widely used. Yes, exactly. That's a set of vertices. When you're actually in 3D graphics, you have a set of vertices. This is a vertex, 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 vertex. In 3D graphics or in 2D graphics, everything is triangles. So if you want to form a figure from these vertices, you have to say which of these vertices form triangles, and you say it with a set of vertices, a set of edges, for example, between these vertices. Yes, that's what the colleague meant. So yeah, if you want to create some shape, well, not that. I don't want to make that. I want to make this. Whoops, not this. Vertex, 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 vertex. and connections between these vertices. This is connected to this, and this is connected to this. Whoops. And this is connected to this, and this is connected to this. And for example, this is connected to this, and this 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 to this. Yeah, that's how 3D graphics work. And they sometimes fill these triangles with something. That's how 3D graphics actually work. So yeah, that's a set of edges, basically, but not exactly. In 3D graphics, there are no graphs exactly. You could say it's a graph, but it's not exactly a graph. It's not a matrix, so either. It's a complicated matter. It's an array of indexes, normally, and each three indexes mean a triangle. It's two arrays. One array of vertices, one array of indexes, which vertices make triangles. Okay, that's not that important. How can we make a graph? Well, first option, child nodes for a graph. I wouldn't make a graph like this. Personally, I wouldn't make a graph like this. How I would make a graph? I'd make a list of vertices, and each vertex will have a list of neighbors. That's it. That's a graph. What's this? I can't tell you. I really don't care what that is. Well, you could implement a directed graph with a list of vertices which have a list of connections. Same thing. This is some representation which you could try to decipher. I'm not sure what it does. So, breadth first search and depth first search for a graph, same thing as in a tree. It's just not go to the children, but go to the neighbors. And one additional thing to have in mind. When you're traversing a graph, and this is important, when you're traversing a graph with depth first search or breadth first search, you always have a visited array. You keep an array with the number of vertices in your graph, and for each index in that array, you say whether that vertex is visited or not. And you only visit non-visited vertices. Because in a tree you can't have visiting already visited vertices, because in a tree you can't have more than one connection to one vertex. But in a graph you can have several connections to that vertex. So it's very important to say whether you visited a vertex already. So when you're doing breadth first search and depth first search on a graph, the only difference is that you say, once you get to a node, you say that that node is visited. Once you visit that node. And add and visit nodes only if they are not visited. Basically, this pseudocode should explain how these things are done. It's not very complicated, especially with breadth first search and depth first search. So yeah, a depth first search recursive traversal. What do? The easiest traversal of a graph. If the node which we have to visit is not visited, then you say it is visited, you print it, for example. You could not print it. And for each child or for each neighbor of that node, go to that node. Call the function traverse with DFS. That's it. Traverse each free node for each free node. For each free node, traverse the first free neighbor for each free node. That's the formulation of DFS. And repeat that and that and that again. Okay. So yeah, that's how you traverse a graph. I think we have a demo. Yes, we have a demo. Demo. Demo is something else. Okay, so we have this bastard of a graph over here. And we have this traversal function. What does it do? It calls itself for each of the nodes it finds free. And yeah, you could start with an integer node. You could start... Yeah, that's a BFS. What do we do in BFS? We use a queue. What do we do in a DFS? We use a stack. Same thing as in a tree. Not really any need to repeat it. What do we do if we want to do it recursive? We do DFS, and we call we call it self at the same moment at which we push in the stack for the non-recursive DFS. So in the non-recursive DFS, push in the stack. For the recursive DFS, call the function again, the method again. Okay. So we create some kind of graph over here, and we say traverse that graph with BFS starting from vertex 0. And then do the same things, but with DFS again at vertex 0. And yeah, some other stuff. Yeah, traverse again. Do some visited stuff. Not pretty sure what this thing does. Bool visited equals new bool of, yeah, just wasting our time over here. Not sure why this thing requires an additional array. It could keep its own. Oh yeah, because it has to have a pointer to the array on which it works, because we can't define our array at each step. Because here in traverse DFS, for example, we use a stack, and this array, when we define it here, it will be the same through all of these operations. And for traverse DFS recursive, if we create an array here, it will be recreated each time we enter the function, the method. That's why we take an array on which to work, and that's why we create it. What? What? We can have what? Yeah, we could put it. We could put the used array in the class. That's an option, but that would be additional memory if we don't want to traverse our graph. That's a matter of decision making, not really of the algorithm. So yeah, traverse it with this array, start these things, and I initiated the wrong project, and this is a startup project. Whoa, what did I do? I closed it. Start it again, breadth first search. So it does something, so probably the 0 vertex is connected with 3 or 3 and 6 and 3, 6 and 1, etc. We could see our tree. That's how breadth first search and depth first search basically work. And they're guaranteed to visit all of the vertices in a graph, and if they don't, that means that the graph is unconnected. If there are unvisited vertices in a graph after you start a DFS or a BFS, then that graph is unconnected. Guaranteed. Absolutely guaranteed. So yeah, recursive DFS and stack DFS. This is DFS traversal with stack. Okay. Changes the order somewhat changes the order, but still visits all of the vertices. Not really. Your order in visiting isn't that important. That's how you traverse a graph. You could try out these things at home. Try out the one with trees, try it out with graphs. Same thing, absolutely the same thing. There is no difference, except for the visited array. Okay, where are we now? What did we learn today? Something, I hope. Yes? The folder system is a tree. If you consider shortcuts part of the folder system, it's a graph, yeah. But the folder system is basically a tree, because that's how the computer traverses it when it searches for information. It traverses it like a tree. And those things, well, if you want to consider them as folder structure shortcuts, shortcuts are just a command, go to there. They're not really part of the structure.
Pointers.
Yeah, they're just some pointers. You can always define a graph which is absolutely connected, meaning that each and every vertex is connected with each and every other vertex if you think of a rule. For example, your rule is shortcuts are also connections. But basically, you could consider it as a tree. Networks are graphs. Again, not guaranteed. There could be a central server and 5 other computers connected to that central server but not connected to each other, and that's a tree. And that's a graph also, but it's a graph which is a tree. So, trees, recursive, each node has sons eventually, or parents, one of them, either sons or parents. Children parents, daughters, whatever you want to call it. Binary search trees, ordered binary trees. Binary trees, what are binary trees? Trees with at most 2 vertices at each node. 2 children at each node. Balanced binary trees have not a weight, this is a height of logarithm of n, where n is the number of vertices. Graphs, well, trees are graphs which don't have cycles or loops or whatever you call them. Graphs can be directed, undirected, etc., etc., etc. Trees can also be directed, undirected, weighted, connected, not connected. In the terminology, it says that unconnected trees are a forest. So yeah, unconnected trees are forests, and unconnected graphs are just unconnected graphs. Unconnected graphs are don't know what. So both, because trees are graphs, both trees and graphs can be traversed with DFS and BFS. When you're traversing trees, you're not really obliged to use a visited array if you have connections only from the parent to the child. If you have the other way around, if you have connections from the child to the parent, well, that's not exactly a tree, but even if we call it a tree, then you will have to use a visited array. And for graphs, always use a visited array. If you're not sure whether there are connections backwards and forwards, and whether there are more connections to one vertex than one, then use a visited array. So play with this stuff, play with DFS and BFS, try them out, try to program them, play out defining a graph with a list of vertices, define it with adjacency matrix, define it with a set of edges, and try and program DFS and BFS on each of them. That's a good idea. I'm not sure if it's in the tasks, but you should do that. It's very useful, so you can learn how to do it in different situations. Because in different situations, different representations will be optimal. Okay, so any questions? Yes?
How do you implement this, the edge weight you talked about?
Oh, how do you implement edge weight? In these data structures, in adjacency matrix, I think it's clear. You just write 5, for example, instead of 1. For adjacency list and a set of edges, you have to create your class, for example, edge class, or something else. For example, in an adjacency list, you won't have which vertex you're adjacent to, but you have a structure of which I'm connected to, this saying 2, and this saying value, for example. And you use these. For a set of edges, you use beginning, these are structures. This is beginning, this is end, and this is value, for example. Again, a structure with these 3 things. That's the idea. Okay, any other questions? SQL server? Yeah, it's a graph. It's a graph. Primary keys in tables. Tables are vertices in the graph, and primary keys are connections between these tables. Keys. Exactly. They're implemented in SQL Server. Yes, BFS and DFS are implemented in SQL Server. Basically, anything having anything to do with databases, all types of databases are graphs in some way. But not only graphs, but graphs with additional characteristics. Okay, anything else? Okay, don't hear any questions. So, we'll stop the recording, and that's it for today. Bye-bye.